So the first thing I did, which doesn't really affect you all because you attend, it was requested that I better label the videos, which I did, except for these first three. I've now got them labeled by section. Oh, I got to label that one too. These are out of order. There we go. Okay, so I've got them labeled by section so you can more easily find the content based on what we did. So this, the dates, of course, match mostly what's in Canvas, or they're off by one because of the one day we missed. So thank you. I forget who it was that suggested that. Thank you for suggesting that. Why is this so slow? There we go. So that's one thing. The other thing is in your course now, there is a Respondus quiz that is for you to test the technology for when we take the actual midterm, and the midterm will be on Monday. Is today Monday or Wednesday? Yeah, so the midterm will be on the 24th. It's not going to show up quite yet. I'm going to put in there. Well, it's not going to be on the 24th. I'm sorry. I'm going to open it on after today. So like you'll be able to take it between the 20th through the 24th. We'll say that. And it will be right here in week 8, which is the week we're in. So this is the Respondus quiz that you need to take. Some of you had already taken it before I set it up with the lockdown browser stuff. So now when you click in here, let's see, it's the highest, takes the highest score. You have 20 minutes to complete it, which doesn't mean anything. And you're going to be prompted to download software that then kind of takes control of your computer and only allows you to go to Desmos. So you'll be given Desmos to work on everything, but it blocks you from all other sources on the internet. And it also records you as you take the exam. So that's to help dissuade people from using things that they're not allowed to use. Any questions about that? Okay, so today we're going to do a review of Unit 2. And we're going to do two things. I'm going to write a reference sheet with you for all of Unit 2. And we're going to work through the Unit 2A review questions. And then your job is to turn in to complete the Unit 2 review B that you'll then submit to be graded by me at some point, just like what we did with the Unit 1 stuff. So let me see if I can find, oh, there's review B. So here we are on page this. Great question, Jennifer. The exam will be, it's not multiple choice at all. It'll be type in the answer, kind of like Alex. And you'll need to type in exactly what you're told to type in. Otherwise, you will get counted wrong. But at the end of the exam, there's going to be an option to submit your scrap work. So what I encourage you to do is to take the exam on a piece of paper, write number 1, write all your work and then your answer, and then type your answer in the computer. Just like you would do if I'd actually printed the exam and handed it to you and you wrote all your work on the printed one. So that's the hope. And then I can give partial credit. Like if you get a question wrong and you're like, hey, I just rounded it incorrectly, I can give you partial credit. Whereas the auto grading stuff for those types of questions will take off all the points if you do it wrong. Okay, so let's, I'm I need to go let my dog in. So I'm going to have you all try this first question, this first page on page 64. I'm going to give you 5 minutes to try this. You see what you can get done. And then from after, when I get back, we'll write up the reference sheet material for all of unit 2. Set a timer for 5 minutes. Okay, I'll be right back. We're on page 64. You all see what you can do with questions 1 and 2. By the way, don't graph on here Desmos, right? Do this in Desmos. Okay, that was 5 minutes. How'd you all do with number 1? Mostly I'm interested in what did you write for X? Love it. Yeah, that's a key concept with time, specifically with years. You're doing that in your project. For task 2 of your project, you should have 0, 3, 6, 9, 12, 15, 18, et cetera, et cetera. Okay. And then from there, it's just like smashing in decimals, right? Hopefully that's clear for everyone. I just for review's sake, because you have to be able to do this for the midterm and the project, I'll remind it and show you. Click that plus sign, put in the table, type in your X values, and then type in your Y values. And then to get a nice view, click the zoom fit, and there's the graph. You can zoom out and do whatever if you want, if you need the zeros or whatever. So what did you all say then when looking at the scatter plot, looking at the graph of the data? What did you say for what this tells us about the average yearly income? Noting that the x-axis is year and the y-axis is income. So like we could come back here and actually type that in, right? Income year. That's it. It's going up over time. And you could probably, since we know all of Unit 2, you could probably say it appears to be a linear increase. So income increases, and you could say linearly. Good. Okay, how'd y'all do with number 2? Anyone get the equation? If not, maybe we should write up our reference sheet first. That's what I did in my in-person class, and that seemed to be helpful for students. Okay. Okay, Jennifer. Love it. So where that's coming from, if anyone here is wondering, is that the general equation of a linear, the general form of a linear equation is y equals mx plus b, one of the forms. This is called the slope-intercept form. And the slope is a rate of change. So Jennifer has correctly noted that 0.1 per minute is a rate. In fact, it's a unit rate. And that an initial cost is a fixed starting value, which is exactly what our B value is. I think it's important to note what X and Y are going to represent. X is going to be minutes, and Y is going to be cost. And so what Jennifer has written is totally right. Y equals 0.1x plus 1. And 0.10 is fine too, either way. Awesome. Okay, so this is like the model of the verbal description we have here. So then how do you figure out the cost after 35 minutes? Okay, for those of you that don't know where that came from, this is an X value, right? Remember how we said X represents minutes? So we're just plugging that thing in, 0.1 times 35 plus 1. This is 3.5 plus 1 is $4.50. Okay, how about how long? Gotcha. Yeah, 140 minutes. Ooh, how did you get that? Well, this is a Y value. Go ahead, Jennifer, talk to me.
I did it complicated. I know what you're gonna show is, yeah, that's not the way I did it.
Oh, what'd you do? Tell us.
I couldn't remember how to do it the way that you're about to show, so I just did 10 cents times 10 is $1. You need 14 because you got the plus 1. So 10 times 14 is 140.
Oh, that's not complicated. That's awesome. I love it.
But yeah, it was just easier for me to figure it out that way than trying to remember how to do it in the equation form.
So in the equation form, there's like the algebraic way, which is like this, and then you solve this like old school algebra. It's an algebra 1 problem that you probably never had to do since your freshman year of high school, or sophomore, or whenever you took algebra 1. The other thing you could do is the graphical method, which is my favorite. And you have to know how to do the graphical method when solving the exponential equations. And so that is, we take these two equations and type them into Desmos. Let me just start a whole new blank graph. So we type in y equals 15, and then y equals 0.1x plus 1. And then we just find where these two things cross. Now, if you look at my graph, I can't see them. So I'm just going to zoom out a little bit. I know y equals 15 is way up here. Zoom out a little bit more. Oh, here they are. There they cross. There's the 140 that Jennifer, that you logicked your way through. Okay, go lay down for a nap, sweet girl. And so there's our 140 minutes. That's the graphical method. Now, if you are someone that loves algebra, what you would do is subtract 1. There's that 14 that you were reasoning your way through, Jennifer. And then you're like, oh, how many 10 senses do I need to get 140? What you could do if you're a calculator type person is you divide by 14 by 0.1, and there's your 140. Or think 140 times 0.1 equals 14, either way. Awesome. I should put the units on these, minutes. Okay, let's pause this part and let me write up kind of a general overview of Unit 2. What I did in the in-person thing is I told everyone, take your paper and fold it in half, hot dog style, and make this line in the middle. And Unit 2 is about 2 concepts: all things linear versus all things exponential. And there's overlap between the two things, and there's things that are also very different. So distinguishing between the two is a big part of Unit 2. So first, we might write out the equation. That's y equals mx plus b for the linear model, or the linear equation. For the exponential equation, that was y equals a times b to the x. Now, I used function notation in class. Our textbook used it too, and it happened to be, in my opinion, quite useful in Desmos. And I would like you to at least be aware of function notation. So that's using like f of x, g of x, h of x, something of x, to write out the equation. So those are the 2 forms or 2 ways you could write it. And then for each of these, we were interested in the parameters. Like, what do those mean? So for the linear equation, we've got slope. And slope is literally this m value. And it is a change in y over a change in x. Our textbook had us working through the slope formula, y1 or y2 minus y1 over x2 minus x1. I'm not particularly worried about that. I just want you to know that it's a change in y divided by a change in x. You should note that this is a rate. And back from unit 1, we talked about rates. In section 2.2, we talked about rates a lot. And oftentimes, it's a unit rate. And then you need to know how to interpret this. Then the other parameter is the y-intercept. And this thing, this is the one that most students get wrong because they don't write it as an ordered pair. It is an ordered pair, and you should think of this as an initial value. And what you need to be doing with these, with both of these, is interpreting them in context. So you're using the words that describe X and Y and telling me what the slope is telling us. So for example, in the problem we just did, here's the slope. The interpretation is that for each minute we ride the scooter, the cost increases by 10 cents, which sounds really cheap. Now, exponential parameters are a little bit more complicated. So we have this B value that can be two different things. It's a growth factor. If B is greater than 1, we call it a decay factor. If B is between 0 and 1. And then for either of these, we can calculate the rate. Oh, cool, you found it. Which is B minus 1. So it becomes decay. If it's a negative value, it becomes, it's considered a growth rate if it's a positive value. Now, this rate is different than this rate here because the exponential rate is a percent change. So you should be thinking new minus old divided by old from unit 1. That was percent change. And this is a number that's multiplied a repeated amount of times versus over here, this rate is added a bunch of times. And then we've got the y-intercept. And in this case, it's 0, a, and it is the same thing as the linear y-intercept. It's just the initial value. That's all it is. So the amount at the beginning of the problem, whatever that is. Okay. This is what you need to function with word problems. If I hand you an equation, you should be able to identify the different pieces and tell me what they mean. If I give you a description of a scenario, you should be able to write the equation. And then in all of those cases, you should be able to do calculations given values for X or Y. The next thing that happened is the Desmos stuff. And what these are regression equations, which are the same thing as models. All right, so it's either of those two words means the same thing. So in Desmos, if you think it's a linear model, well, actually, I should first write that what you're going to do in Desmos is create this table, x1, y1. If you think it's exponential, you're going to do y1 tilde ab to the x1. If you think it's linear, you're going to do y1 tilde mx1 plus b. That's the code you type into Desmos to get a regression equation or a model, linear or exponential model, from a data set. So maybe I should even label that this table is a data set or table of values. How you determine which is the better equation depends on the correlation coefficient. So there's this correlation coefficient. And that is a number between -1 and 1. The thing that's closer to 1 or -1 is the R value. Excellent, Jennifer. Yeah. Now there's one thing you have to do. in Desmos, there's this button called log mode. And for what we're doing in this class, you've got to check that log mode to get the correlation coefficient. And then the other thing that I think is important is understanding the basic shapes of the graphs. So, I guess the other thing is to note that this values close to -1 are decay models. Values close to +1 are growth models, either linear or exponential. We can then draw the basic shapes of the graphs. There are two primary ones for linear. There's three we're interested in. Here's a growth model. Here's a decay model. Linear. So this is a positive slope. This would be a negative slope. Exponential has two basic shapes. So here's a growth model for exponential that corresponds to b values greater than 1. Here's a decay model for exponential that corresponds to b values between 0 and 1. And then the last thing that we do here that turns out to be pretty useful is solving for x. What that looks like graphically is you're going to have some sort of exponential model. I'll pretend it's growth. It could also be decay. And then some sort of y value, and this is the solution. So you're going to graph those two things. You're going to graph y equals some number and y equals ab to the x with the numbers a and b in there, and you'll get this basic shape somewhere in the graph, or one that looks like this, and you're going to find where those two cross. The x coordinate of that intersection point is the solution. It's the same thing I just showed you here with two linear equations finding their intersection point. It's just with linear models, you don't like you can solve them without having to graph. The exponential, you have no hope of solving them unless you understand logarithms, which would be awesome if you did, but there's no need. Okay, any questions on that? All right. So let's jump back to this. I'm going to give you what I was doing in my in-person class is I was giving people 5 minutes per question, and then we talk about it. So this is now page 65. Take 5 minutes and see if you can solve this question. Set a timer for 5 minutes. Okay, y'all, that was 5 minutes. Anyone know the slope for A? Or do y'all need more time? Nailed it. The number times X is the slope. Now, I'm going to do two things that you may or may not have done, but I think it's helpful to do this. I'm going to make sure we all understand what X means. It's years after 1990. And Y is the number of households in millions with internet access. So I'm just going to put households. Okay, so then if I identify the slope, like Jennifer's done correctly, I would write it like this. But actually, because we're going to interpret it, we need to know what the fraction it is. This is a unit rate. So really, we should think about this as 6.76 divided by 1. And the denominator is years, the numerator is households. Right? So what is the sentence that interprets that slope in context? We should say in millions here too. So, oh, there we go. So be a little careful with that because that statement sounds like an ordered pair, meaning a static or a fixed value. You've got the pieces needed more or less. We just need to turn it into a rate. So say, no, you got to go take a nap. Go take a nap. And when Emma comes home, you can go out. Okay, so what's happening here is for each year after 1990, yeah, there's the language of rate. So mine's gonna be a little similar because so for each year after 1990, households with internet access that's not how you spell internet increases by 6.76 million households. Do y'all get the subtle difference there? Million households. Awesome. Good, good. Okay, so then the y-intercept is not this, right? Y-intercept is 0, 14.9, and then Maya, what you said nails it. In 1990, because 0 corresponds to the year 1990. In 1990, there were 14.9 million households with internet access. I'm just going to say with internet. And I'm going to spell it correctly now. Internet. There we go. All right. How's that feel? This is the very thing you're doing on project 2 when you are to interpret the parameters. If the best model to fit your data was linear, you would be saying this, a similar statement for the slope and a similar statement for the y-intercept. All right, quick question. What is the model? When I say according to the model, what am I referring to?
The equation?
Yeah, good, good. I want to make sure that's clear to everyone. That's an important thing to keep track of. We're referring to this when we say this. So according to that, what's the answer? How many households had access in 2010? Well, the question then becomes, Nice, Jennifer. All right. So where'd you get the 20 from? So this is an X value, but why is it 20?
Because it's 20 years after 1990.
Nailed it. And if you're not sure how to get the 20, just literally subtract the 1990 from 2010 and you get, oh, we're working with 20 years, and then we're going to plug that in as the X value to the equation and get whatever the number is. Let's see, were you kind enough to tell me? 150 million, love it. And you interpreted it, which you didn't have to, but that's awesome that you did. Which equals 150.1 million households. Awesome. Question D is essentially the same question, except that note that this is a Y value, not an X value. So we're saying when Y is 100 million, what is X in this equation? Now you can solve it analytically, or you can solve it graphically. I prefer graphically. I don't know about you all. Okay, nice. You're crushing it. Now the trick on this one is being able to find it. We need to get to 100, thankfully. Oh yeah, so we got to zoom way out till we see 100. There it is, 12.589. Does everyone know why Jennifer said 2003? Like, why don't we say that the answer is 12.589? And for the sake of time, I'm just going to tell you, we're taking 1990 and we're adding 13 years to it, which gets us to, oh, is it 2013? What is it? Is it 2003? 1990, yes, 2003. Perfect. Good. Okay. Notice on all of this, this question is essentially the same question as the one here, except instead of giving you a verbal description of the initial value and the rate, we gave you an equation and asked you to tell us what it meant given the context. Okay, so you need to be able to go either direction. Be handed the equation, talk about the parameters from the equation, be handed the parameters, write the equation. So question 4, let's do another 5 minutes, except this question C is a little wonky. You see 12 packs of 12-ounce cans are on sale for $3.50. What this really should mean is 1 pack with 12-ounce cans in it. All right. So it's a 12 pack. It's a case of 12-ounce cans, which is very common, that you're being charged $3.50 for that whole thing. So let me give you 5 minutes to play with this problem, and then we'll talk about it. Set a timer for 5 minutes. Okay, that was a hard 5 minutes. How are we doing? Do y'all know what a unit price means? Okay, I'll just talk through it. So what you're being asked to do here is calculate a rate. And hopefully you're remembering back from 2-2 that this means divide. And the order that these things are written matters. In other words, what we're writing here is dollars divided by liters. So we're told that 2 liters of Coke cost $1.67. So we're going to put the dollars on top and the liters on bottom. Turns out that's not a unit rate. So you also need to know that when we talk about a unit something, we want the denominator to be 1. So the way to do that is just take 1.67 and divide it by 2. You get $0.84 per 1 liter, or 84 cents per liter. Nice. I like the not rounded value better than my rounded value. If you are a unit rate shopper, these numbers are often given to you on the sticker in the stores. Check them every once in a while. They may not actually be right. Mistakes do happen. Okay, so what does it mean? It costs, like, we're just rewriting. This is like the slope thing. Each liter costs 83 cents and 5/10 of a cent. Or you could say it costs $0.835 to purchase 1 liter, which of course you can't do. But you could also talk about it at a unit rate. Yep, love it. Love it. Good job. Okay, this next one, if we can get past the confusing language, you discover we want the same thing, only this time it's dollars per ounces instead of dollars per liter. So we're going to put in there the 350. That's the number of dollars we're spending. And we're going to do the 12 cans times the 12 ounces to get the total number of ounces we're purchasing. Nice. So that's exactly what Jennifer's saying, 0.02430. Oh, sorry, baby. Let's see. So that's dollars per 1 ounce. All right, then we're like, hey, what's the better deal? Can is the better deal. How'd you do it? There's multiple ways we could do this. We could convert this. Go ahead, Jennifer, tell us.
See, I didn't really write out a bunch. I just knew to do, because you're obviously buying it in 2 liter form. You're not buying it by the liter. So 67.6, that's how many ounces is in a 2 liter. You'd need like 2.5 roughly, which is going to be more than $3.50. So I didn't actually like work it all out. I just kind of did it in my head and just.
Yeah, I mean, that's your brain work. Yeah, you did it. Yes, you did work it out. That's awesome. So so what I did in the day class or the in-person class is I just converted this ounce rate into liter rate. You're totally right. I love that you needed, you're like, hey, I need about 2.5 liters. So I would multiply this by about 2.5 or something. And yeah, it ends up being cheaper this way. What I would like to remind you all is that this is an equivalency statement. So this goes back to unit 1. And we're going to write a conversion factor to convert this into dollars per liter so we can directly compare the two rates. We could also go from liters to ounces. But since I've chosen it this way, I would just do 33.8 ounces in the numerator, 1 liter in the denominator. These cancel, and we're going to be left with dollars per ounce. And then we have a number that we can compare directly. So 0.0243 times 33.8. Notice the denominators are all ones. So it's costing us 82,134 $0.82 per 1 ounce. You can see that that's a little bit cheaper. It's not a lot cheaper. Roughly a cent cheaper. Cans are better. Excellent. All right. Similar problem, same idea. You're going to calculate some unit rates, and you're going to do a conversion factor. So see if you can do kind of like what you did here in number 5. Set a timer for 5 minutes. Okay. So I'm just going to jump in, unless you all want to take over too. Notice same language as above, miles per minute. So we're going to take the total miles, 26.2. We're going to take the total minutes, 1, 2, 3. And there's a rate. Got to do that division to get the unit rate. So just type in Desmos or your calculator, whatever you use, your thing. And you got what this guy's doing in terms of miles per minute. That's approximately 0.213 miles per minute. You may recognize this problem from the worksheet. I think this is the 2.4 worksheet. But we simplified it a little bit by giving you the number in minutes. Okay, the second one, notice it's the same thing, except we want minutes per mile. So we can take either one of these fractions, it doesn't matter which, and just flip it. And then we have minutes per mile. Love it, Jennifer. Yeah, so you're just typing that in Desmos, 1 divided by 0.213, or 123 divided by 26.2, and you get 4.695 minutes per mile. If anyone's a runner in here, you will understand that this guy is cruising. That is in my opinion, a super fast mile. And he's doing that for an hour and a half, a little over an hour and a half. So what does this answer mean? Well, we're just stating what that is. He is running 1 mile in 4.695 minutes. And really we should add, he's averaging a speed of 1 mile in 4.695 minutes, because this is a rate, but I guess I'm not going to be too picky about that. And he's doing this, he's maintaining this pace throughout the entire 26.2 mile run. This is no longer the fastest record. I wrote this worksheet a couple years back. This was in 2014, and it was just broken this year. Actually, it's broken a couple times. So if you Google the fastest marathon, you'll find that. All right. So now we're saying, what's the speed in meters per hour? Well, we've got miles per minute. We've got a bunch of different options. What we don't have is meters and hours. So I'm just going to take, the unrounded value, the 26.2 miles over 123 minutes. And this is the rate I'm going to use. And our job here is just to convert it into meters per hour. So notice that meters is a measurement of distance, hours is a measurement of time. So I've got my fraction written with the correct types of measurements in the correct spots. I've got the distance in the top and I've got the time in the bottom. You can do this all at once by using these equivalency statements to write conversion factors. My in-person class seems to prefer as a group that you do it piece by piece. So maybe let's change the minutes into hours. So if I want hours in the denominator, I'm going to put hour here. And I know that there are 60 minutes in 1 hour. That does it, right? Minutes go away and we get miles per hour. So we could just go ahead and multiply that out and get our answer. And that's 26.2 times 60 divided by 123, and we get 12.78 miles per hour. Okay, we're halfway there. Now we just have to turn the miles into meters. So we could go from miles to feet and then feet to meters, or we could go from miles to kilometers and then kilometers to meters. Doesn't matter which. I think what I will do is go miles to feet and then feet to meters. So if I want to get rid of the miles, I know I need a mile in the denominator of my factor. So this cancels here. And this becomes 5,280 feet. And then if I want to get rid of the feet, I'm going to put the feet in the bottom, 3.28 feet in the denominator, and 1 meter in the numerator. And notice those cancel, and we're going to left with meters per hour. How are we doing? Y'all following, or is this crazy talk? Okay, talk to me. Where did I lose you? That'll do it. So did you get what happened here? Do you get why this fraction is here? Or what I did with the, maybe I should start way back at the beginning. So first I picked this rate as the one I'm going to start with. Okay, good. And then I converted that into miles per hour here. So then all I have to do is take these miles and turn them into meters to get what I want. Well, I need 2 things, and you could go, there are 2 routes to go. Option A is maybe going from miles to kilometers, kilometers to meters, or from miles to feet and then feet to meters. So I picked to go from miles into feet and then from feet into meters. This fraction gets rid of the miles and gives us feet per hour. This fraction gets rid of the feet and leaves us with meters. And then our final answer is just going to be this, whatever this thing is, multiplied out, it will be in meters per hour, which is precisely what we were asked to do. I happen to have the number. It's a little bit insane. 20,573 point, I believe that was 84. Nope, it was 47 if I round to 2 decimal places. 47 meters per 1 hour. You are most welcome. You might have slightly different numbers here for this number of meters. Like if you used, say, this rounded number, it'll be a little bit different. Or if you use the kilometers route, you will have a slightly different number. They'll be close to this, but it could be, 100 meters off or so. And that's just because of rounding. Cool. Okay, so on the midterm, expect a problem where you're going to be finding some sort of rate and then converting that rate into some other unit measurement. If you need a keyword, this was dimensional analysis. We did it in section 2.2 and I believe section 1.6. Okay, last 2 questions. So here we're looking for a model of best fit in both of these problems. So whenever you're given a data set and you're asked to find a model of best fit, that means you are doing this. You're using Desmos and you're going to type both of these equations in, to see which one is better, and you determine which one is better based off of the R value. So let me give you 5 minutes to try it. I don't know how many of you have, let me just close this. How many of you have, oh no, I didn't want to do that. Oh well. How many have number pads? But I can quickly type in the data and I'll share that graph with you. We could race. If you get it done before me, then so let it be. So I'm going to know my passwords. So just in case you don't want to have to type the table, There it is. All right, now 5 minutes. See if you can't solve this whole problem. Set a timer for 5 minutes. So model is the same thing as regression equation, which is the same thing. We had the same language here. So what you're doing is writing code in Desmos. And these are the codes you're using. You're using this code for the linear model, this code for the exponential model, and then you're picking based on this criteria, which is the better fit for the data. Don't forget that. So, right, so you can look at the data set. So I click the zoom fit and you can look at it. And to me, it's like, oh, that's obviously linear, right? Like if you look at the shape, it looks like this, as opposed to some little curvature like this one. But you need to make sure, because it could, sometimes these things can be tricky, and sometimes the exponential model might be a little bit better. So you're typing in here y1 tilde mx1 plus b. There's the linear model. Now, it's not given to you in the form that you need. You have to take this and write it down correctly, which is another thing we've been practicing a lot. But yeah, there it is. And then the other one is y1 tilde ab raised to the x1. There's the exponential. Again, don't forget to click this log mode. And when you compare these R values, 0.9994 versus 0.9805, the linear is better. If you just look at the graph, I think you can see it too, that the data values are all closer to the line than they are to the exponential curve. So how we write that down, that's an important thing. You're going to be doing that in the project, on the midterm, you're doing it here, you did it in some of the worksheets. You're going to write y equals, it says round to 2 decimal places. So 0.44x plus 14.64. Now, I prefer function notation. So I'm going to write it in function notation. Oops, if I can get the correct eraser. F of x equals this. So yeah, that's the model of best fit, or the equation, the regression equation, however you want to say that. And then the R value, which also known as the correlation coefficient, that's this 0.9994, and it says that the linear is the best model. We'll just say linear is a good fit. Remember, we need to be close to 1. If it had been 0.7 and the exponential had been like 0.6, then the linear model is the better model, but it's not a very good fit. So it kind of tells you a couple different things. It tells you 2 things. So then the y-intercept, you need to be careful. This isn't 100% clear. It should say interpret the y-intercept in context from the model, not from the table, right? Because there is a y-intercept in the table, but our model has a different one. So the y-intercept here is 0.14.64. Now, the interpretation here is what is the x value, depth, the y value is pressure. So we could say something like at a depth of 0 feet, pressure is 14.64 pounds per square inch. How are we doing so far? Is that, did you all have this? Just in case you didn't, here's my updated link. With the new, with the codes typed in there. A quick note here, whatever's up here in the table also needs to correspond to what you're typing in the code here. So X1, Y1 isn't like that important. It's whatever it is here. It's just every time you make a table, it puts in a subscript. Like if I open another table, see how it says X3, Y3? There's now, we would need to type those numbers in for the code to get the new model. All right. Note, this is not an exponential, so we don't need to worry about the growth rate. This is linear, so we got to interpret the slope. I think it's very helpful to think about the slope as that fraction. It is a unit rate. Desmos will always give you unit rates. That's just how numbers are reported. So the denominator is feet, the numerator is pounds per square inch. So we might say pressure increases by 0.44 pounds per square inch for each 1 foot increase in depth. Ooh, that was a bad way to say it. Maybe a better way would be like if depth increases by 1 foot, pressure increases by 0.44 pounds per square inch. How y'all doing with that? E says use your model. Okay, so what we're saying is ignore this for the moment and use the model for when the pressure for a depth of 100. Well, I'm going to do this thing where I write down my model. We need to do this anyways. I'm going to write it in function notation. You don't have to do this, but I think it's helpful. It's handy. And then if I'm wanting to, this is an X value. So if I'm wanting to figure out the pressure, I'm just going to calculate F of 100, meaning I'm going to plug 100 in for X. So if you type things in a function notation, you can literally type F of 100 and you get 58.64. And that is pounds per square inch. Another way, if you're not using function notation, or the other way is just to say Y is equal to this. Well, and then F takes us back to unit 1 and whether or not you remember the relative error or percent error formula. From what I recall, it's estimate minus actual divided by actual. Turns out you could also do actual minus estimate divided by estimate, and that's a perfectly acceptable calculation. The key here is making sure you understand what's what. So anytime you use a model to calculate things, that's an estimate. Anytime we're grabbing things from a data set, an observed data value, that's the actual value. That's the correct value. So in other words, what we're calculating here is what's the percent error from our model. So if I follow the pattern I have here, the estimate is 58.64. We subtract from that 58 and we divide by 58. And then of course, multiply that by 100 and you get the relative error or the percent error. I'm getting approximately 0.011. Oh, whoops, I didn't multiply it by 100. So times 100, it's about 1.1% above, 1.1% over estimate. If you do the subtraction the other way around, in other words, if you do 58 minus 58.64 divided by 58.64, you get a negative 1.09. And that says that the actual value is 1.09 below the estimated value. Okay, do it again, y'all. One more. Same thing. Create a table of values. I'll type them in for you. So here's the length of the table, and it's the exact same questions. Find the model of best fit. What's the R value? Tell me the y-intercept. Tell me the slope or the growth rate. Calculate a value. Calculate the relative error. This one has one new question. Solve it. So let me give you 5 minutes, and then we'll see if you've got it done. Set a timer for 5 minutes. Okay, yo, that was 5 minutes. All right, so I entered in the two models, the codes for the two models. Here's my look. Pretty clearly exponential growth is the better model. If you look at the R values, yep, that's also true. I mean, it's almost a perfect fit. If this was exactly 1, it would be exactly exponential data set, and all the points would be accounted for based off the model. So we got to make sure we correctly write it down. Note we're doing 2 decimal places. So I'm going to use g of x for this one just because it's a different function than we already used f of x. So 36,163.1. I like to use parentheses sometimes for multiplication, 1.08 raised to the x power. Now I've rounded that b value quite a bit by, well, I guess it's not too much, but that does change things. That will throw off, it's an estimate on top of an estimate. So our R value, here it is, 0.9999. Exponential is a good model, right, is what it's saying. Now, in your project, most of your models are going to be quite awful. That's just the nature of it. Stocks are far too complicated to be modeled by linear or exponential data. In fact, when people work with stocks, they're going to use statistical models that have all kinds of different things going on in them. So don't be alarmed if your R values are bad. We had a couple in the worksheets that were bad. Y-intercept. This one's a little different. Recall from the notes we wrote at the beginning that the y-intercept is the 0, b value. So it's the number times the other number that has the exponent on it. So in this case, it's 0, 36,163.1. And this is year 0, 1930. So we're going to say in 1930, we'll just say cane infestation was 36,163.1 square kilometers. Now, again, that's different than the actual value in the data set, but that's expected, right? Models are predictions or estimations or approximations of actual data values. And we use them to kind of talk about trends and look about, maybe try to make predictions. So don't be alarmed by that. Note for D, this is not a linear model, so there is no slope to talk about. Instead, we're talking about this B equals 1.08. That's the growth factor. Recall in the notes here that we can find the growth rate by subtracting 1 from the growth factor. And the reason I suggest you think about that is that you already know how to interpret a growth rate because it's percent change. You did that in unit 1. So you're going to explain the when, the what, and the how much. So in this case, we're going to say from 1930, maybe we don't want to start. We'll just say that. From 1930, infestation, cane infestation in Australia. And we can say it 2 ways. You can either say it has increased by 8% per year. And maybe we should just get rid of this and say since 1980 or since 1930. Or we could say that infestation has increased by a factor of 1.08 since 1930, either one. I like this one a little better personally. I think it makes a little more sense, but it's up to you. You can, either one is correct. All right, then we're supposed to use our model to figure out what is the cane infestation in 1960. Well, that means we need an X value, and 1960 is not the correct X value because that would be 1,900 and 60 years after 1930. So really, we need this 30. And then, nice, Jennifer. Yeah, exactly. Then we're going to do G of 30. So I'm going to go ahead and type that into Desmos. Where are you, Desmos? Here you are. So first I'm going to type in my function, G of X equals 36,163.1 times 1.08 raised to the X. And then we're going to do G of 30. And there it is. 363,896.87 square kilometers. That's what our model predicts it would be in 1960. Oh, hey, look, we have an actual value here. Here's what it actually was. Let's calculate the percent error or the relative error. So that's estimate, just like the previous problem. Here's the estimate. Here's the actual. So we're going to do 363,896.87 minus 352,900 all over 352,900. Again, you could do it the other way as well. Just make sure whatever you're dividing by is the same thing you're subtracting. So because I don't want to type all that, I'm just going to use G's of 30 minus 352,900 divided by 352,900. And yeah, we're getting 3% off. So it's actually a little worse of an approximation than our last one, 3.12%. So it's a 3.12% overestimate. All right, the last one is that important question that the only way you can solve is graphically, which is why I said sketch the graph. I don't know what this maximum and minimum is all about. Oh, I see. The maximum minimum we're meaning is like how you found the graph. So what we're going to do is we're saying when does y equal 100 million or 1 million. Oops. So we're going to type this in. I already have G of X typed in, and we're just going to see where the two intersect. So this is a little bit of a challenge to find. Oops, I got 10 million. But if we think carefully about it, it shouldn't be too hard to find. Notice, well, here's the 1 million, right? We could, if we did zoom fit from our table, we have a pretty close view. We're at 800,000. So if we zoom out a little more, we'd hit the 1 million mark. And there's that intersection. It's 43.135. So X equals 43.135. If I were to sketch that graph, it looks like this, and this thing is 43. Blah, blah, blah. Now, this isn't the answer, right? We need to add this to 1930. So this, we would just do plus 1930, and we get the year, which is what you were asked. It says, in what year will the area be? And that would have been 1973, based on our model. That's the prediction, which is long past. We could check it out and see, did that actually happen? Was the model a good prediction? Okay, that leaves you with the Unit 2 Review B to do as your practice and turn in for a grade. So you'll see a couple rate things, you'll see a graph thing. Don't worry about like showing me that you drew that. Just make sure you know how to draw it. And there's two graphs here. You can graph both of them at the same time. I'll show you that in Desmos. If you want more than one graph, you just click next to it and you can type in another set of data. And you get another graph, right? So you can graph two things at once. Ooh, that's an interesting looking thing. And then the midterm is going to open tomorrow. It'll be a Respondus proctored midterm, meaning you can take it anytime you want from tomorrow up till Monday of next week. And it's cumulative. So it'll be a mixture of this stuff with the Unit 1 stuff. What I would encourage you to do is look back over the Unit 1 Review A and Review B. There is a video on YouTube labeled with that reviews on it. And we also wrote up a reference sheet in that review. So I would find all that. And then you're going to have access to Desmos through your laptop, through your computer that you're taking the exam on. And you get to write 3 or 4 pages of handwritten notes of anything you want that you think would help you. And when I say anything you want, what I suggested you do is write this stuff down. All right, any questions you'll have? Awesome, Jennifer. Have a great weekend. And we'll see you on Monday.
I have one more.
Yeah, go ahead.
So I'm trying to do my unit project and I can't get my Desmos like graph to get on my unit project. Is it okay if I just like download it and like take a screenshot of it and then put it into like the unit project as like a screenshot?
You can do that.
Like not on Excel?
Yes, you can screenshot it into Excel. The other thing you could do is just click this button here where it says share.
Send you the link.
Yeah, you can copy the link and dump it right in Excel, and then I'll just click the link and it'll open up your graph.
Okay, thank you.
But to do that, you have to have an account and you have to have saved it, I think.
Okay.
Maybe not. Awesome. Yep. Other questions you have? Maya, did you have a question?
No, I'm good.
Okay.
All right. Thank you.
Awesome. All right,
Bye.
y'all.